Welcome to episode 2 of AATED Project. What we have here in episode 2 is to discover the proper interfacing of external circuit into the Arduino Uno board. LEDs like this one, the red and the blue LEDs, into the Arduino Uno module. I will be replacing the LEDs with these 4-channel relays, 2-channel relays, and 1-channel relays. You may have in mind why most people make use of the LED as their first interfacing to any microcontroller. In many publications or many YouTube examples, they make use of the LED. So the LED will gonna be the subject matter, and we will take a look at it, how it is interfaced into the Arduino Uno. Alright, let's go back into my small working room, and I'm going to show you the first interfacing to the Arduino Uno, which is the LED. Let's see the circuit in my board. Let's see how this external LED is interfaced or connected to the Arduino Uno R3. The red LED is interfaced or connected to pin 12 in a current sink configuration. The blue LED is connected to pin 8 in a current source configuration. In their datasheet, pin 12 of the Arduino is equivalent to pin 18, or this is P4. Also, pin 8 of the Arduino is equivalent to pin 14, or DO. I will be following the naming convention of the Arduino Uno. That means to say that I'll be naming it as pin 12 instead of pin 18, and at the same time I'll be calling pin 8 instead of pin 14. In our program, we must declare that the bit port pin 12 of the Arduino Uno R3 must be an output, meaning to say that it controls the red LED. In the same thing, we need to instruct the microcontroller that pin 8 is used as an output to control the blue LED. To light up the red LED or turn on the red LED, we must instruct bit port pin 12 to go low. Let's see what's going on inside the microcontroller in the current sink configuration. We can imagine that the pin 12 of the Arduino Uno R3 is connected internally into the microcontroller. It's just like a switch. Then you can select high and low. We are controlling an LED, a red LED, and the rule of the LED is that the anode must be more positive than to its cathode in order for the red LED to light up. In our program, if we instruct pin 12 to go low, that means digital write at pin 12 is low. We can see that the cathode now is connected into the GND, and there is a continuous flow of current. So the equivalent circuit therefore is this one. We have plus 5 volt going down to 560 ohms resistors going to the red LED and to the ground, and there is a closed loop. So the red LED is now turned on, and the current flowing through it is about 5.3 milliamperes. This 5.3 milliamperes is controlled by the resistor 560 ohms. Since it is connected in the current sinks, the 5.3 milliampere is going inside into the microcontroller. If you want to get details on the voltage distributions of the external circuit, the resistor R1 560 ohms and the red LED, here it is. The voltage drop at the resistor is 3 volts, and the forward voltage of the red LED is 2 volts. Totaling 3 volts plus 2 volts is equivalent to 5 volts, which is basically the same as supply. So what happens if the microcontroller we instruct it in the wrong way? Say for example, we instruct pin 12 to go high, then the LED will not light up. If you can see in here, we get plus 5 volt there going into the anode, and the cathode is also connected to plus 5 volt. So there is a closed loop, but the rule of the LED in order to light is that the anode must be more positive than the cathode. In this case, the anode is less positive with the cathode because of the dropping resistor here, and therefore there is no flow of current. So virtually we can imagine that the current flowing now into the LED is 0. That is why it is not light up. And here is what happening for the current source configuration. In order for the blue LED to light, we need to apply a positive voltage more positive than the cathode of the LED. So we can instruct the microcontroller through the program digital write at pin 8 to be high. If that will happen, we can imagine that the switch inside the microcontroller is connected to the supply, which is 5 volts. In that way, there is a closed loop from the positive supply going to the microcontroller into the LED to the resistor, then to ground, and there is a flow of current, and then the LED will light up. The current is 4.1 milliampere, which is going out from the microcontroller through pin 8 of the Arduino Uno. What will happen if we wrongly instruct the microcontroller to go slow? See at pin 8, when we instruct the microcontroller using digital write at pin 8 low, then the anode is basically at GND. That means to say that the anode is basically the same as the cathode. Therefore, the LED will not light up and the current flow is 0. Let's see the actual circuit in the Arduino compatible board. You can see that the two LEDs, they are turned on now. The red LED on the left and the blue LED on the right. Let's see the sketch. The sketch is another name for the Arduino program, and this is the initialization, which define the microcontroller output, like pin mode. The built-in LED is used as an output. The pin 12, which is also used an output to control the red LED, and the LED control 8, that is the name of the Arduino output, which is I declared earlier. I made the pin 8, the alias is LED control 8. So I'm saying that the LED control 8, which is basically pin 8 of the Arduino, is an output to control the blue LED. Here is the main program. The built-in LED is connected in the current source mode. So in order to light up the built-in LED, you need to instruct it to high. While the red LED connected at pin 12, it is in the current sync mode, so you need to instruct it to go slow. The blue LED, which is connected to pin 8, The alias name for pin 8 is LED control 8. You need to instruct it to goes high because it is connected in the current source mode. So that's it. That's the simple program to control the external LED circuit that I have connected with my Arduino Uno compatible board. I modified the program so that the blue LED will blink, and here is the instruction. I just alternately control the blue LED connected at pin 8 with a high and low instruction. Let's download the program. Uploading it and then uploading. There you are. You can see that the blue LED is blinking at the rate of 1 second. 1 second on, 1 second off. And here it is. The blue and the red LED are alternately blinking at a rate of 0.5 second or 500 millisecond. Let's download that. And there you are. Done uploading. And here you go. You can see the red and the blue LED are alternately blinking at a rate of 500 millisecond. It's easy to control the LED, the external LEDs that I connected with the Arduino Uno. Of course, you can only control them correctly if you know how they are interfaced into the Arduino Uno. Hey guys, sorry for the delay of episode 2 of the AATED project. It's just because I was called for a real job here, jumping from Shenzhen, China to here in Europe. Currently I'm here in Paris. Okay, so let's take it away. Continue episode 2 with the correct interfacing of a tact switch. This time I'm going to add a tact switch, and then I'm going to replace the 2 LEDs with the relays. Take it away. Continue the episode 2 of the AATED project. What I have done so far is to program the Arduino board to control an external device, and this device is the red LED and the blue LED alternately blinking at a rate of 500 milliseconds. Now, I want to do differently by programming the Arduino to accept an input command from me. How I'm going to do that? By means of the switch. This switch here. This switch is a normally open tact switch, which by default it is logic high. When I'm going to depress the switch, it goes to logic low. Here is the schematic diagram of interfacing this switch into the Arduino Uno board. As I mentioned, I choose AO. The internal connection to the microcontroller is at pin 23, or this is labeled at PC0. By checking the data sheets, I found that the PC0 have an internal pull-up resistors, which is programmable by programming the internal switch to connect it to VCC. Now, you may see a very strange here, which I put up an R3, which is 22K, as a pull-up resistors. I did not make use of the internal resistors. The reason why is that at this moment, I don't know how to program the Arduino Uno to make use of the internal pull-up resistors. That is a drawback to me, but along the way, I'm going to know how to program the internal resistors so that I can omit the R3 here. For the time being, for my purpose, I'm going to make use an external pull-up resistors R3, which is 22 kilo ohms. The purpose of when I'm not pressing the SW1, which is NO or normally open switch, the initial state at bit port A0 is high. The reason is that bit port A0 is tied up to R3, which is pull up at +5 BDC. That means to say then that it is high or plus 5 volt. When I depress SW1, what will happen is that bit port A0 will be forced to connect to GND. That means to say that the logic level changes from high to low, or GND. In my program, my detection will be logic low. I can instruct the Arduino board that my detection when I depress the switch is logic low. Before that, I must instruct the Arduino board that bit port A0 is used as an input, not an output. It is an input because it keeps watching the changes of logic at SW1 from high to low or low to high. One thing important to note about tech switch or switch is that there is what we call as the bounce. When I just press the switch, the logic level from high to low is not an immediate. See this diagram. You can see that when I depress the switch, I can imagine that the logic level will goes from high and then it's bouncing and then it settles down to low. Just like you drop a ball and the ball will keep bouncing until it will rest on the ground. Now, be careful when you're detecting a switch because of this, the bounce in here, the bouncing switch, then the bit port AO may interpret this as a logic high and logic low. Logic high, logic low, logic high, logic low. And that means to say that it may give you a false detection of the switch. So be careful that you will going to detect the presence of logic low after such like maybe 20 milliseconds. That means to say that in the program, probably in here it's logic high and then you give like 20 milliseconds and then detect the presence of logic low so that your detection will not be misleading or your detection will not be false. Let's see the schematic diagram combining the switch SW1, the red LED, the blue LED, and I included the built-in LED which is connected to pin 13. What I'm going to do in here is that the built-in LED will keep blinking at a rate of 500 milliseconds. The red LED and the blue LED will initially turn off. It will turn on when I'm going to depress SW1. That means to say, when I press SW1, the red LED and the blue LED will turn on. When I press SW1 once again, the red LED and the blue LED will turn off. Let's see that. Let's see the simplified timing diagram of the things that I want to do in the program. Let's start with the built-in LED connected at pin 13. As you can see in here, the diagram showing that it goes logic low, logic high, and become fast, logic low, logic high, low high, low high, low high. So it means to say that the built-in LED is blinking. This is bit port A0 where the switch SW1 is connected. What will happen is that initially it is high because no one is depressing the switch and the blinking LED at pin 13 is at normal rate. When I depress SW1, pin 13 LED becomes blink fast. And once I release the key, or when I release the switch SW1, pin 13 LED blink at its normal rate. Now let's see the two LEDs connected at pin 12 for the red LED and pin 8 for the blue LED. When nobody is depressing the switch, the blue LED is not turn on, as well as the red LED. When I depress the switch connected at A0 and release it, and that's the time that the blue LED and the red LED will now turn on. You can see here that they were turned on based on how this LED is connected. Pin 12 is connected as current sink mode, and pin 8 is connected as current source. So the logic level is entirely different. Red LED is turned on when it is at logic low, while the blue LED is turned on while at logic high. So in other words, from this timing diagram, we can say that whenever I depress the key, the pin 13 LED blink faster. When I release SW1, pin 13 LED becomes normal rate. When I depress the key, the two LEDs, red and the blue, will turn on. When I depress it once again, the two LEDs, the red and the blue, will turn off. Whenever I depress the key, the LEDs will turn on. Depress it once again, the LEDs will turn off. Turn on, turn off, turn on, turn off whenever I depress the key. You can see again the pin 13 LED is blinking at 500 milliseconds, and when I press and hold, that is 3, 2, 1, the flashing rate will increase. You can see it is flashing already, but in my naked eyes I can see it. And release the key, press once again to light up the two LEDs, press once again to turn off. There you are. What I'm going to do in here is that I'm going to replace those two LEDs, the red and the blue LEDs, with this 2-channel relay board. Here is the relay that I can find in the live market. From the marking on the relay body, it says 05 BDC. That means say its operating voltage is plus 5 volts. There is a bingo because the Arduino operating voltage is plus 5 volts. The control interface is a 2.5 mm header, and it is labeled as GND, in, and VCC. This is where I'm going to connect the pins of the Arduino. And here is the relay interface. I can see here it is single pull, single draw. Here is my procedure to understand the relay better by subjecting it electrically. It says that the relay, the operating voltage is plus 5 volts, so I set my power supply to plus 5 volts. That is plus 5 volt DC. And then supply it to its VCC and GND. These two here are the controls. The way to find out whether it is logic high or logic low is put it into plus 5 volts and nothing happens. Now change it to logic low and see what happened. There you are. You may hear the click and then the LED turn on. There you are. So this relay board is activated with the logic low, and when the relay is active, the current consumption is 0.079, that is 79 milliamperes. That is just for one relay. What I'm going to do in here is that when I want to activate this relay, I'm going to press SW1. If I deactivated again the relay, I just have to press again SW1. So how I'm going to test that one? I'm going to make use of a multimeter, set it into the continuity testers. That means to say that this 2-channel relay board, when it is activated, this multimeter will continuously beep. That means to say that the relay is basically switched on. Here is the actual modular board interfacing the 2-port relay into the Arduino Uno. This is another Arduino Uno compatible that I'm using. The relay is off and the meter is not beeping. I will press the switch now and the relay is turned on and the multimeter is beeping. I will press it once again and the relay turned off, multimeter is not beeping anymore. Press it on, press it off, once again. Press it on and you can see that the LED, the built-in LED is blinking fast. Once I release the switch, it goes back to normal blinking and it turns on the relay. Press again, it turns off. Let me include the basic circuit diagram of the relay module to complete AATED episode 2. This block here is the relay module, and this is the simplified basic circuit diagram. It composed of an optocoupler, transistors, and the relay itself. Let's see the configuration of the optocoupler. This one here is basically an LED inside connected in a current sync mode controlled by Arduino digital input-output pin 12. In our basic understanding of LED connected in the current sync mode, we must control the LED by sending a logic low so that there will be a flow of current from plus 5 volts going to the resistor to the LED going inside at pin 12 into the Arduino Uno board. So we will go into command pin 12 to go logic low in order to activate the relay. Let me explain further. When pin 12 goes low and the LED will light inside the optocoupler, this transistor here become like a switch. Its collector is virtually connected to its emitter, thereby there is a flow of current from plus 5 VDC going to these resistors, going to Q1, activating Q1 and activated relay 1. What will happen is that the pin 2 and 3 of the relay will be closed, just like a short circuit. By the way, the function of D1 here is to kill the voltage that is developed into the inductor of the relay. You may have seen this circuit before, and it looks like that it has been an industry circuit when using a relay. You always see the diode is connected across the inductor or the positive supply of the relay. But what is really the function of D1? How the diode D1 works? This one. Right. When the relay is not activated, there is no any voltage developed into the inductor of the relay. When the Arduino Uno sends a logic 0, the relay is activated, meaning that the plus 5 volt is impressed or supplied into the inductor. That means to say that it is stored a voltage. Well, inductor can store a voltage. During the time that the Arduino Uno send a logic high, this logic high here, then the relay will be deactivated. What will happen is that the voltage that is stored into the inductor, it will be released into the circuit. To follow the industry standard of connection, we can place the D1 to make it sure that every time the relay is deactivated and the voltage released from the inductor, D1 will clamp it and will kill that voltage, avoiding to spread out throughout the circuit. Yeah, it's TGIS. Thanks God it's Saturday that I have the chance again to make my episode 2 and also play with my Verity. I left it somewhere over there. Just let her to play with the water. I'll show you how I did play with her. Yeah, if you like my Verity, our tag team, and if you like my videos on this stuff, please subscribe to these channels. You make it sure that future videos will be informed. Alright, so thank you once again. I hope you enjoy watching my videos on the D-Stuff channels. And if you haven't subscribed it, thanks for subscribing. Have a nice day, guys. And always remember, it's D-Stuff here. Episode 3 of the AATED project is about the features, the block diagram, and also starting the man-machine interface of the project. So it's gonna be a boring episode 3, but we need this technical specification because as a designer